Welcome to Lecture 37. This is our second body composition lecture and, of course, the last lecture of the semester. Our final topic is going to be the two-component model of body composition. And we'll take a look at 4 different methods that specifically can be used within this two-component model. We'll spend most of the time on the hydrostatic or underwater weighing, but we'll also take a look at air displacement plethysmography, bioelectric impedance analysis, and the sum of skin folds, as these are also very common methods of use in body composition research. So things to think about for today's lecture. What is the two-component model? That is, what are the two components? It's fat mass and fat-free mass, right? What does underwater weighing actually measure? We'll take a good look at that today. What is Archimedes' principle? Know how to calculate percent fat using Archimedes' principle and the Siri equation. What is air displacement plethysmography? What is BIA and how does it work? And how does the measurement of skin folds predict percent fat? So let's first jump into underwater weighing. No pun intended. And here's a photo of someone doing the test. So you can see there is a tank. The subject is sitting on essentially a bench that's attached to a scale, and then the technician is recording the underwater weight. The protocol is really straightforward and fairly simple. The subject simply sits down in the water, exhales completely, and then goes underwater. When the bench is essentially still and the needle on the scale is not moving around too much, the technician will just say, okay, come up. And you do that a few times and you sort of take the average of all the measurements. However, it's actually harder than it looks. And the main reason is that most people do not like to be underwater while having blown all of their air out of their lungs. And so when you go underwater, you need to squeeze all the air out of your lungs that you possibly can to get rid of all of the air except for your residual volume. And then sit underwater for another, I don't know, maybe 5 or 10 seconds. This is not a big deal for anyone who's comfortable in the water, like you swimmers out there, but for people who are not comfortable in the water, this is sometimes can be a pretty traumatic experience, and they don't like it at all. And that's where air plethysmography comes in, and for some people might be a better technique, but we'll get to that later on. So after doing the underwater weighing, you'll get a weight of the person underwater, and then what? What does that actually tell us? Well, this is where Archimedes' principle comes in. First, a bit about Archimedes. He was a Greek mathematician and scientist and inventor. He came up with how to figure out the surface area of a sphere. He also invented some really cool mechanical devices like the Archimedes screw, which is a way to raise up water out of a well or a river. You can look that one up. But he also came up with Archimedes' principle, which is a way to really figure out the density of certain objects. The legend goes something like this. The local king had received a crown that was supposed to be solid gold, but he wasn't quite sure, and he suspected the craftsman may have added some silver in it. So he took it to Archimedes and said, can you tell me if this is completely gold or not? And you need to figure it out without destroying the crown. So he thought about it a while and then figured out if he could weigh it underwater, that would essentially test the density. And so he was able to determine, no, it actually did have some silver in it. It wasn't pure gold. So anyway, the principle goes something like this. The first point here, if you immerse any object in water, it is going to be buoyed up. Some of its weight is going to be supported by a buoyant force from the water. So everything, when you lower it into the water, is going to weigh less than it does on dry land. And Archimedes figured out that, I'm going to underline it here, the buoyant force is equal to the weight of the fluid that is displaced by the object. And so that's shown in the example down below, where you can see you have the 7-pound weight, and then when it's lowered into the water, now it only weighs 4 pounds. Well, that shows you that there is some 3-pound force that is pushing up and supporting the weight of the object. Also, that the water that has spilled over into this dish here is going to weigh 3 water. So the weight of the water that's displaced is equal to that buoyant force. If we go to the second point here, it says if the weight of the water displaced is less than the weight of the object will sink. And so this helps us determine whether an object will sink or float, and essentially it's based on density, right? Remember that density equals mass over volume. So water has a density of 1 because, well, it depends on the temperature, but at 15 degrees Celsius, I think it is, 1 kilogram of water will take up exactly 1 liter. And so if something has a density of greater than 1, then it will sink. And if something has a density of less than 1, it will float. And that's shown in the lower right, where you can see a ball, a steel ball, will sink because the displaced water weighs less than the ball. However, a ship with this hull will float because the volume of water you're displacing is actually going to weigh more than the ship itself. So that's Archimedes' principle and a way to look at density and the relationship between mass and volume. So let's take a look about how we might use that in actual underwater weighing of humans. And so we have two subjects in this example, Craig and Brad. We can see that they are the exact same height and weight, 1.88 meters, and their mass is 93 kilograms each. However, look what's different. Their underwater mass, Craig weighs 5 kilograms, but Brad weighs only 3.5. So the buoyant force pushing up on Brad is greater than the buoyant force pushing up on Craig, which means, of course, Craig now has a smaller volume than Brad does, which means his density is going to be a little bit greater. Craig's density is 1.075, Brad's is 1.057. If we then use the Siri equation, that will get us to a percent fat for Craig of 10.4 and Brad for 18.4. So next, let's take a look at how that calculation is done. If you follow along on page 425 of your textbook, that might help you go over this equation. We'll start with the basic equation, density equals mass over volume. Now we can expand on this and use our measurements that were taken on the human body. In this expanded equation now we can see that the numerator, m sub a, means mass in the air. So that's the person's body mass just on a regular scale. And now in the denominator we have mass in the air minus the mass underwater. And that's going to be divided by the density of the water. So let's take a look at this denominator in a little bit more detail. And that would just be this portion here. Where do we get these numbers? And so if we extrapolate this out, essentially what we're doing is this is how to figure out the volume of the body. We know the mass, because that's up here. And now how do we figure out the volume? Well, if we take the mass in the air minus the mass underwater, we know the difference is going to be that buoyant force pushing up. Since we know the weight of the body that has been displaced equals the weight of the water that's been displaced, we then can figure out the volume. Why? Because volume equals mass over density. And so essentially the top of this gives us the mass of the water divided by the density of the water, and that'll give us the volume of the water, which is equal to the volume of the body. So that takes us back to the figuring out the density of the body, which is, of course, the mass over the volume. Before we go any further on the calculation, though, we now need to correct the denominator for two more volumes that are in the body. One is the volume of the residual volume in the lungs, that's called VR, and the other is the volume of air in the gastrointestinal tract. There's always air in these spaces, and you have to subtract that out because those, of course, would be buoyant forces and not contribute to the body's density at all. So we put those in the denominator. There are some techniques to measure the residual volume. There's some rebreathing of nitrogen and helium techniques. You can also just take a percentage of the vital capacity, or sometimes people will just use an estimate based on body height. And for the gastrointestinal tract, it's usually just estimated at around 100 milliliters. So now let's take a look at an actual example. So here's a person who weighs 88 kilograms. Body mass underwater is 5.2 kilograms. In this case, the density of water is 0.9944. The person's residual volume is 1.2 liters, and the volume of the GI tract is 0.1. So let's go through and do the calculation. Let's first set it up. So 88 is our mass in the air, and that goes in the numerator. Then in the denominator, of course, we'll have 88 minus 5.2, the mass in the air minus the mass underwater, divided by the density of the water, 0.9944, and then subtracting the GI volume and residual volume. This, of course, is going to equal now 88 is going to remain in the numerator, and now we get 82.8 divided by 0.9944 minus 1.2 minus 0.1. So first let's leave the numerator as it is and let's tackle the denominator. And so now we'll go down here, and this is going to be 88. We'll leave that, and this is going to be divided by, let's simplify first. Remember, order of operations, you got to do division first ahead of addition and subtraction. And so 82.8 divided by 0.9944 is 83.2663. And then we still have to leave then the minus 1.2 minus 0.1. Now when you're doing these calculations, I would suggest go out to 4 decimal points, because you'll see it makes a really big difference when you start narrowing down, when you get down to the density, because of something like 1.07 density versus 1.065 actually makes quite a bit of difference when you put it into the Curie equation. So now we'll simplify this, and we get 88 divided by 81.9663. And that equals, well, we'll put it down here, 1.0736. And that, of course, now is your body density. Now that we've determined the body density, now we go back to the Curie equation, plug it in, and you'll get a percent fat. So let's erase all of this, and we'll start again with our density equals 1.0736. So I've just written in the Curie equation, which is percent fat equals 495 divided by density minus 450. So in this case, we would say 495 divided by 1.0736 minus 450. And that equals 461.0656 minus 450, and then of course that would then equal 11.0656, and then you can just simplify that to about either 11% or 11.1% fat. So there's an example from start to finish on the underwater weighing technique. It's all about plugging in numbers and using the right equations. So keep practicing that. Plug in different numbers on your own. I've also given another example on the PowerPoint slides that are also posted. So take a look at that if you'd like. Now let's go on to the rest of the methods for using this two-component model. And the first one is called air plethysmography. And the most common, the brand of this is called a Bod Pod, and it's a fairly popular instrument used in the field of body composition. I should start by explaining plethysmography. A plethysmograph is a device that measures body volume. You can measure in a specific organ, like the arm or the leg or a whole body. This is a whole body plethysmograph, and it uses changes in air pressure. And so you would go sit in this pod, you shut the door, it's airtight, and then there's a small pump that can change the volume of air inside the chamber. And so by doing that, it can figure out your body volume. And so this uses the same sort of principle of underwater weighing, but just a different method to determine your body volume. So once we know your body mass and your volume, then of course we can figure out density, and then you would just simply use the Siri equation. Next, let's look at bioelectric impedance analysis. This is also called BIA. You've probably done a version of this in your health and wellness or lifetime fitness class where we use the handheld device. A better technique is to use the whole body BIA, and in this picture you can see there are 2 electrodes placed on the hand or the wrist and the other 2 on the foot and ankle. The technique uses a current. It sends a current through the entire body. It's not perceptible to the subject. And then the other electrodes will pick up the current and see how much impedance or resistance there was to the flow of electricity. The principle behind this is that lean tissue contains lots of water, and so it is a really good conductor, whereas adipose tissue or fat is an insulator. It does not conduct well, and so it can predict the percent body fat. The error rate for this is a little higher than with underwater weighing or air plethysmography. For BIA, it's about 3.5% to 5%, whereas for underwater weighing, only 2 to 2.5%, and air plethysmography is about 2.2 to 3.7% error. Finally, let's go to the sum of the skin folds, and this is the measurement of skin fold thickness, and essentially you're measuring subcutaneous fat at various sites around the body. There are hundreds of equations that can be used for this that utilize different sites for measuring the skin fold thickness. The one shown here is at the triceps. You can also use the chest, the thigh, the abdomen, the scapula, the calf, and different methods, different equations will use different sites. Most of these equations are population specific, that is for different races, and they're also sex specific, so there's male and female. They have different equations for different ages because we have learned that the way we store subcutaneous fat will change over our lives and is certainly variable from person to person. And that's one of the problems of using skin fold measurements, because of course you're assuming that the subcutaneous fat storage that we can measure then is a good predictor of whole body fat, and that may or may not be true. The benefit of skin folds, of course, is that it's easy to measure and you need very little equipment, just skin calipers. And so you don't need the underwater weighing tank or the scale and the inconvenience of putting subjects underwater. This is pretty simple and it's pretty fast. I'll finish up this discussion with just a little explanation of how skin fold the system was developed. Initially, researchers wanted to figure out an easier way to estimate body density, and so they realized, well, we can use subcutaneous fat as an estimate of overall body fat. And so the initial studies took subjects and used underwater weighing as the standard to get body density. So you'd have, say, 100 subjects. You would figure out their body density through underwater weighing, calculate the percent fat, and then take a bunch of skin fold measurements all around the body, and then develop an equation in which you can run it through a regression and statistics, and it'll spit out an equation in which the skin fold measurements will match. We'll develop a system so it will spit out a percent fat that will match your underwater weighing. So for this reason, some people have called skin folds a doubly indirect method. That is because, of course, underwater weighing is an indirect method of measuring percent body fat. I think it initially was based on the use of cadavers, and then used underwater weighing and the Siri equation to determine percent fat from body density. And now we've based our skin folds on underwater weighing, and so we're basing one indirect method on another indirect method, and so skin folds have sometimes been called doubly indirect. The error for skin folds is also a little bit higher, and estimated to be about 3.5% error. And so what that means is that if the error is plus or minus 3.5%, let's say you got a value of 20% fat. Well, then you would know your percent fat is somewhere between 16.5 and 23.5%. So now that we've covered all the methods of measurement, let's figure out how to make sense of it all and what it means. So here's a chart for body fatness for health and fitness. These are explained on page 428 of your book. And so your recommended percent body fatness for health, so this is your general health. You can see we have young adults, middle-aged, and elderly, anywhere from 8 to 22% for young adults for men, 20 to 35 for women, middle-aged a little bit higher, 10 to 25, and then women 25 to 38, elderly 10 to 23 for men, women 25 to 35. Then there's a second standard that's given, and this is for fitness, and I think what they mean here is for high fitness level, people who exercise a lot. You might expect a much lower body fat. And so for men, 5 to 15, for young adults, and women 16 to 28. I think these values are sort of the low end of the values, about as low as you'd want to go. And below that would be considered, I don't know if it's unhealthy, but less than optimal. So finally, the last topic I'll discuss is the consideration for body composition and performance. How does it affect exercise performance? As we all know, most of the sports that we engage in and that we watch, they are highly dependent on strength and power, and therefore you'd want to maximize your fat-free mass and therefore minimize your fat mass. And so obviously, things like football, baseball, basketball, softball, and some of the power events for track and field, right? Shot put, discus, hammer throw, javelin. These things where power is paramount and even the additional body mass might be an advantage rather than a disadvantage. However, the other side of that coin, it might be undesirable for any athletes in which you have to move the body through the air, like jumping sports, so long jump, pole vault, high jump. Clearly you're at a disadvantage if you have a greater mass. Similarly, we can look at the consideration of body fat and the relative body fat, and usually it's going to be detrimental to performance. And again, anything in which you're moving the body through space, you want to minimize your body weight and therefore your body fat. So anything with running, jumping, things like that, especially where being airborne is paramount, things like gymnastics, right? However, there are some sports where an increase in fat might be an advantage. And there's some listed here. Heavyweight weightlifters, so it lowers your center of gravity and makes you more stable. And then, of course, allows the controlling and lifting of the weights. Sumo wrestlers, of course, because moving mass is the paramount in that sport. And then the other one we typically don't think about is in swimming, because the more buoyant, the higher up on the water the person can swim, that would be an advantage because there's less drag. And on that last point, I'll just end with two photographs. The one on the left is Ian Thorpe. He's a former world record holder in distance freestyle. And you can see he's not especially muscle-bound, is not really all that defined or cut. He looks like just a pretty normal guy, but was a world record holder. Whereas the guy on the right, who's clearly a bodybuilder, would probably not be a good swimmer. He has too much muscle, he is too dense, and he would definitely sink. So fat-free mass and fat mass definitely will play a role in performance. So that concludes our consideration of body composition and also concludes the semester. Thanks for tuning in.